So hi and welcome to this video. I'm going to present the paper, The Complexity of the Distributed Constraint Satisfaction Problem. This is joint work between myself and Victor Dalmau, and this presentation is for the conference STACS 2021. Now, the general question that we wanted to address in this paper was, what can you compute in a distributed system? And because this question is very general, we made it a little bit more specific, and we asked the question, what families of CSPs can you solve in a distributed fashion? And if you can solve them, then how fast can you solve them? Now I'm going to start by defining what a CSP is. So let D be a finite domain and gamma be a finite set of relations over the domain D. Then an instance I of the constraint satisfaction problem over gamma is a triple. So we have three objects. The first is a set of variables, which we call X, a finite domain D, the set that I talked about before, and finally a set of constraints C. Now, constraint is a pair which contains, first of all, a relation from gamma, and then a scope S, which is a tuple of variables from the set of variables, and from, very importantly, the arity of S coincides with the arity of the relation. Now, we say that an instance I is satisfiable if there exists a map mu, which maps variables to elements of the domain, such that every constraint is satisfied. And by this, I mean every scope is mapped to a tuple in the corresponding relation. Now, there is a distributed version of the constraint satisfaction problem, which we call DCSP. This originated in 1992 as a formalization of cooperative distributed problem solving frameworks. So let D be a finite domain and gamma be a finite set of relations over D. Now an instance I of the distributed constraint satisfaction problem over gamma is a quintuple where we have a set of variables, a set of constraints and a domain as before. But additionally, we have a set of agents and a function alpha, which assigns the control of each variable and each constraint to an agent. Now, alpha is surjective, so that means each agent is controlling at least one variable or one constraint. We make some assumptions on the model. In particular, we assume that there are as many agents as variables and constraints, and so in particular, each agent controls exactly either one variable or one constraint. Now, additionally, the original model only allowed for binary constraints. We extend this to allow for non-binary constraints. And of course, if all the constraints are binary, then the model could be simplified a little bit. Now, I'm going to define the decision and search problem for the DCSP of gamma. So we say that a distributed algorithm solves the decision problem for DCSP of gamma if given an instance I of DCSP over gamma. First of all, the algorithm terminates over I, and secondly, at termination, every process correctly states that I is satisfiable, if it is satisfiable, and that it is not satisfiable otherwise. Now, I will also define the search problem for DCSP of gamma, although we will not go into the details in this talk. So we say that the distributed algorithm solves the search problem for the DCSP of gamma if, first of all, it solves the decision problem, and additionally, if the instance, which is the input, is satisfiable, then the terminated state also outputs a satisfying assignment for that instance. And this assignment is given in such a way that every variable process only needs to output the assignment for that specific variable. So it's given locally in a way. Now, a little bit on message passing networks. We say that a distributed network or a message passing network, it consists of a finite set of nodes, which we also call processes, and these are connected to through communication channels. And now these processes can perform three kinds of events. They can send and receive messages, and they can perform internal events, which are any kind of computation, states updates, termination decisions, and so on. Now, we make, again, some fundamental assumptions on our network. First of all, we assume that communication is synchronous. That means that every algorithm will proceed in rounds, and no messages from the following rounds are going to be sent until all the messages from the previous rounds are received and processed. The second assumption is that the network is anonymous. This means that either the processes do not have an ID, and this might be because they lack the hardware to create an ID, or that they do have an ID, but they are unable to share it with the other processes in the network. And this might be due to privacy reasons or, again, hardware issues in the communication channels. The final assumption is that the network is deterministic. So every process in the network runs the same algorithm, and this algorithm is deterministic. These assumptions altogether are very important because they imply that it is impossible in general to elect a leader on such a distributed network. There are many counterexamples, very simple, that can show that this is impossible. And this is important because if we were able to elect a leader, then all the information about the CSP could be gathered to the leader, and the leader could solve the CSP in a centralized fashion. So then the classification results would be the same as those for the centralized CSP. However, since we saw that this is not possible, there is space for new and interesting results here. Now, how do we encode an instance of the DCSP framework in a message passing network? This is very simple. We consider an undirected bipartite graph, which we call the factor graph, and its vertex set is given by the set of agents of the DCSP instance, while its edge set is very natural. We have an edge between a variable and a constraint, if and only if that variable participates in that constraint. Now, this factor graph is a labeled graph, so every edge has a label, and in particular, it is labeled with the corresponding relation of the constraint that is incident to that edge, and it is labeled with a set which contains the positions in the scope of the constraints where the corresponding variable appears. Now, before I go on to state the main result, I have to define polymorphisms. So an emery polymorphism of gamma is a function from the mth power of the domain D to D. And it is a function which satisfies that every relation R from gamma is invariant under the coordinate-wise application of F to any set of m tuples from the relation. So here, basically, if I pick m tuples from R and I apply this function F coordinate-wise, I need to get a result that is still in the relation R. And we say that the function is symmetric if its output doesn't change when we permute its argument. So finally, the main results. The main theorem is that the decision problem for DCSP of gamma is solvable in polynomial time if and only if gamma has symmetric polymorphisms of every arity. And otherwise, we cannot solve DCSP of gamma in finite time. There are no algorithms that solve it. This result can be easily extended to the search problem to show that the classification result in the search case is the same. So DCSP of gamma can be solved in polynomial time if and only if we have symmetric polymorphisms of all arities, and otherwise there are no algorithms that solve the search problem for DCSP of gamma. Now, I'm going to try to give a little bit of intuition on why intractable languages are in fact intractable. But before I do that, I will need to define an additional notion, which is that of iterated degree. Now, the iterated degree is a feature which basically gives an equivalence relation on the set of vertices of a graph, and in our case, it's going to be an equivalent relation on the set of vertices, on the set of agents of the network. So the concept of iterated degree originates from graph theory, and the iterated degree of a vertex can be easily calculated by using the color refinement algorithm, which is also known as one-dimensional Weisfeiler-Lehmann algorithm. This is very simple. So the 0th degree of a vertex is defined to be its degree, so the size of its neighborhood. And then for any k greater than 0, the kth degree of a vertex is just the multiset of k-1 degrees of its neighbors. So for example, here I have a graph. Every vertex has degree 2, except for these 2 vertices here, which have 3 neighbors, so they have degree 3. Now, when we iterate, we get a partition which is given by this iterated degree. And in particular, for example, I have this vertex here, which had 3 neighbors, 2 of degree 2 and 1 of degree 3. So its first degree is going to be 2, 2, 3. It's easy to see that this is a stable partition. That is, we cannot iterate further to get more refined partitions. Now, the Weiss-Feiler-Lehmann algorithm was originally used as a heuristic for testing graph isomorphism. In particular, if we have 2 graphs that do not have the same iterated degree sequence, then we know that they are not isomorphic. However, the opposite is not true. In fact, this algorithm works very well. It works on almost all graphs, but it is known that it fails also very badly on very simple graphs, such as regular graph. So here I have an example of 2 graphs which are free regular. So they will have the same iterated degree sequence. However, it's easy to see that they are not isomorphic because the left one is bipartite, but the right one is not. And now we extend this concept of iterated degree to instances of CSP in the following way. First of all, we want to make sure that variables and constraints get different degrees. And so the 0th degree is just a symbol which differentiates variables from constraints. And now, because we are calculating this iterated degree on a labeled graph, or factor graph, and we do not want to lose the information that comes from labels, we set the kth degree of a variable, or well, of a node in the network, to be the multiset of tuples containing the k-1 degrees of its neighbors and the label that connects that node to that neighbor. And we say that two nodes are degree equivalent, iterated degree equivalent, if and only if they have the same iterated degree for all natural numbers k. Now we make a very important observation here, which is that if any 2 nodes in the factor graph are equivalent with respect to iterated degree, this can happen if and only if any terminating decision algorithm over the corresponding instance outputs the same decision at the corresponding processes. And additionally, if we have 2 instances of DCSP of gamma, which have the same iterated degree sequence, so the same multiset of degrees, then on both inputs, any terminated decision algorithm must report the same decision. And now the idea to show that languages that do not have symmetric polymorphisms of polarities are intractable is to find 2 gadgets which are basically cannot be distinguished by any distributed algorithm, but they differ with respect to satisfiability. So one of them is satisfiable and the other one is not. And this would imply directly that these languages cannot be solved by any distributed algorithm. Now, we couldn't find such gadgets in gamma, in the DCSP of gamma, so we had to construct a new relation. In particular, assuming that k is some integer such that we are missing a symmetric polymorphism of arity k, then we define a relation u of k, which basically corresponds to the set of k-ary polymorphisms of gamma. And now, U can be reduced to gamma via something that I call an EFPP definition. So I'll explain what it is. PP formula, primitive positive formula, or PP formula for short, is a first order formula which only uses existential quantifiers, conjunctions, and equality. And an equality-free PP formula, or EFPP formula for short, is a PP formula which does not use equality. So we are only left with existential quantifiers, conjunctions, and relations from gamma in this case. And there is a very well-known reduction in algebra between structures that are PP definable from each other. And we can extend this reduction to EFPP reductions. So we claim that if a constraint language gamma prime is EFPP definable from gamma, that means all the relations can be EFPP defined from gamma, then if DCSP of gamma is solvable in polynomial time, so is DCSP of gamma prime. And now, so assuming that we do not have these symmetric polymorphisms of arity k, we construct this relation u of k, and I'm not going to go into the details, but we can find 2 instances in CSP of u of k, such that first of all, they have the same iterated degree sequence, and so no distributed algorithm can distinguish between them because of this observation that I mentioned before, that if we have two structures that have the same iterated degree sequence, then every algorithm will output the same decision at every node. And then additionally, we define the first structure to be unsatisfiable and the second one to be satisfiable. So this means automatically that any algorithm will fail on either of the two structures. And therefore, these languages cannot be tractable in the distributed framework. Now, down to tractable languages, I'm going to talk a little bit about the algorithm that shows that tractable languages are in fact tractable. So let gamma be a constraint language that has symmetric polymorphisms of all hierarchies. Then we can show that there exists an algorithm which solves DCSP of gamma in polynomial time. And in particular, it runs in n² rounds. Total running time is a little bit higher because the rounds are not linear. So it has its total running time is n³ m log n. And the maximum message size is also bounded above polynomially by m log n, where m is the number of constraints and n is the number of variables in the network. Now, before I talk more about this algorithm, I need to mention the structure theorem. So this is a result that it also comes from our paper, and it basically says something about the solution space of a CSP instance, any CSP instance. The structure theorem states the following. Gamma has symmetric polymorphisms of polarities if and only for every instance I of CSP of gamma, there exists a satisfying assignment which basically assigns the same value to every pair of variables that have the same iterated degree. And now, finally, given the structure theorem, our algorithm consists of two phases. In the first phase, every process calculates its iterated degree, and this can be done in a very simple way. It's an adaptation of the color refinement algorithm, which I mentioned above for graphs. Now, the naive version of this algorithm only takes n rounds. However, the maximum size of a message which is passed during the algorithm is a little bit large. It depends linearly on the number of constraints. And basically, this is not good because later we will use this, we will need to process these messages in such a way that it will affect also time complexity. So we improved this algorithm at the cost of adding a little bit of time. So we now run over n² rounds. However, we could decrease the maximum size of a message to just be logarithmic in n. And then once every process has calculated its iterated degree, they can use it as an ID to tag their messages. So now the network, in a way, is no longer anonymous. It doesn't have unique IDs, but it has IDs that are unique up to equivalence of degrees. And this is very important because it will give us that basically a distributed version of JPQ consistency, a recent algorithm, solves the decision problem for DCSP of gamma. And altogether, these two phases of the algorithm give us the polynomial bounds that we needed. Now, I'll just try to explain a little bit how this JPQ consistency works. So during the algorithm, every process which controls a variable maintains a set S of X, and this set is a subset of the domain. And it is such that for every solution of the CSP instance, if this solution assigns the same value to any pair of degree equivalent variables, then the value assigned by that solution to that variable belongs to the set. And this needs to be maintained at all time. Now, initially, the set is just set to be the domain for every variable. And at every iteration, we calculate the following set Si of X by taking the previous set Si minus 1 of X and removing all the variables, all the elements of the domain D, such that basically not every variable that is degree equivalent to X is consistent with taking that value D. And now this calculation can be done again in n rounds. So every iteration is going to be consist of n rounds. Just to give you a little idea of how these sets are computed, for instance, here I have 0 in my set Si of x, but there is no path which leads me to 0 in Si of y. So if x and y are equivalent, then I need to drop the 0 from both sets. On the other hand, here I have a path from 1 in Si of x down to 1 in Si of y. So this means that at this point it is consistent that both variables take value 1, and then I will keep 1 in the set. Now, once these sets are calculated, we obtain a fixed point at most n iterations. So these sets can no longer be updated. And now the important observation is that given that gamma has symmetric polymorphisms of polarities and hence it has bounded width, and given our structure theorem that says that if gamma has symmetric polymorphisms of polarities, then every instance must have a solution which assigns the same value to every pair of degree equivalent variables, then we have that JPQ consistency actually decides DCSP of gamma. And it decides it in such a way that depends on these sets, on this fixed point of these sets that are calculated during the algorithm. And in particular, we have that if any one of these sets is empty, then the instance is not satisfiable. And this can be shared, can be broadcasted along around the network so that every variable and constraint is made aware that the instance is not satisfiable and outputs the right output. On the other hand, if all of these sets are non-empty, then we can say for sure that the instance is satisfiable and that actually one satisfying assignment belongs to these sets. And this completes the proof of the main theorem and also of my talk. So thank you very much.